So it is a subject called sound synthesis and analysis. Traditionally, I don't do much analysis because it's kind of higher level. But the good news here is that the group is so small that it is nearly individual education.
Exactly.
And especially because I've been teaching sound synthesis for 15 years now, I have a lot of videos online as well where I go into some details on stuff. So I'm kind of past the point of, going through the history, the textbook, the kind of thing that you can read in many places, here in many places. But I'm more interested in poking you guys and seeing like, okay, do you understand this? Do you know what this is? Okay, that's good. Let's go on. Do you understand this? So it's almost like the only thing we're gonna do is we're gonna have exams. Every class is an exam, and obviously not such that you get a mark, but such that I can help you and identify where you might have something missing and focus a bit on that, explain that to some extent. It all depends on you, really. So, because typically once you're here, you already know something about sound synthesis, right? So that's why it can be very boring if I start from the very beginning and go through all the motions. And also because I live in Bristol in UK, and I'm here today and tomorrow. We have classes, and should be back in April for a week.
April, okay.
So I'm not in the country, but I will organize some online sessions. I guess you guys are fine with that. Just get onto Zoom, whatever link, and then we can continue. But I will first introduce the structure of the course, such that you know what's ahead, what do you expect. So we have Sound Synthesis 1 and Sound Synthesis 2. This is 1, which is a theoretical course. The second one is the practical one. Okay, so typically we run the practical in Super Collider. You guys know Super Collider?
Yeah.
Do you code any programming languages at all? Like maybe JavaScript, C++?
I used to learn C++ and C#, but I can understand the basics.
You understand the basic YouTube? Basics of programming?
Not really. No,
Not really, not really. So that might be tricky. I will talk to Balázs if he wants to, we could also study, but that's actually coming for the second half. We could also start using Max MSP, which is more accessible. Have you seen that before?
Exactly.
With the boxes connecting, so it's not
Fast.
syntax. It's a bit more accessible, so you might enjoy that more. So we can use that also for the practical stuff. Also, it is useful for me to already know which direction we're heading, because if I show examples, it makes sense to show them on the platform that we're going to use in the second half. So probably I will talk to Balázs as well, because actually also among the Hungarian students, the majority would prefer a more accessible tool like Max MSP. But Balázs is like, no, teach them programming. Teach them, if they don't get it, fine. But, do your best to put it across. So I keep teaching them in Super Collider. Now, this first half is theoretical, so actually there is no real need for implementation. However, I must say that the most interesting things I've learned from experimenting, from having a question come up that I don't find an answer to,
Mm-hmm.
and trying things out. It's like, okay, but wait a minute, does it actually, how is your maths, guys? You know any maths numbers?
I'm kind of.
You kind of? You see, that's tricky, because if you don't know maths and you don't know programming, then this might be a challenge, because that's the basis. It's like trying to learn a language without being able to speak or something like this. And that is because we are focusing on understanding the foundations and not on twisting the knobs. All of you can twist the knobs, you download the synth, you find out what it does. So this is not what we're going to do. We're not going to do knob twisting. We're going to do deep theory here, which will definitely help you with your knob twisting, because you will know better what to expect behind certain knobs and what type of interaction there may be between different parameters. Now you will study with me, if everything goes well, psychoacoustics as well, which will again be another scientific topic that supports your artistry. Okay, so my opinion is that, you know, it is very tricky to teach art, but it's much easier and maybe even more worthwhile to teach the tools that you may use to produce your art. And I will teach those kind of subjects. So fairly technical, you know, academic stuff. So first half is the theory. Now I'm very flexible and open in terms of how you want to do an exam. So typically I offer, so the topic for your exam in this first half is going to be to research deeper into a certain synthesis related subject. So maybe you pick one synthesis technique and you go for it. You know, you dig it up in more detail. And in terms of how you present it, I'm totally open. So there's a lot of students who do like making a video. So you can do a 5 to 10 minute video where you present this, maybe you play in a few sounds. Obviously, if there is some kind of text going or a presentation in the background. I mean, you've seen a lot of these things, obviously. The nice thing about the video is that, you know, if you do it well, you're already putting yourself out there and you can, you know, make it available on different platforms, whatever. So that's the kind of the modern option. A lot of students go for that. I mean, some of them don't do it with much detail and it's just camera like this and you talk it. In fact, in China, my students, they also have video presentation. It's that they're just reading something on a single page. You know, it's a bit boring like that. So obviously, if you want a good mark, you know, you just push it. On the other hand, I'm not teaching video editing, so that will be up to you. So that's one option. The other option is typically a written, essentially essay type submission. The topic is the same. You choose a synthesis technique that you analyze. Typically, I also take some precaution in terms of asking you to tell me what you want to research. Okay, because very often some students would be like, okay, I'm going to do the FM synthesis. And they say Chowning invented FM. I was like, really? Well, he didn't really invent FM. He did the first, you know, chip that did it. FM was in radio transmission 50 years before Chowning, whatever. I was, oh, really? Okay, then. You know, so there are some students who will just, you know, try to get away with the least work possible. I'm happy with that. I was a bit like that as well. I was a horrible student. But I'm a really good teacher, mind you. So that's the second option, the essay. And then come the interesting options. The third option, which is typically my favorite, is oral exam, a viva voce. Because actually in 5-10 minutes, I can really gauge your understanding of, you know, the fundamentals of sound synthesis. So if you choose a viva, an oral exam, it's typically the shortest one. And in the oral exam, I would typically ask a kind of a breadth of understanding. So if you think like, well, actually, I'm not really interested in one specific technique. I don't want to dig very deep into that. But I really want to know a bit about everything. And I don't really feel like, you know, writing about it makes me understand better. Then, you know, the oral exam might be your choice, because that's like, okay, let's see how much you know. We have a quick chat. I'm like, well, typically I start like, okay, I start with the difficult question. If you answer this question, you get the maximum points. And then, you know, oh, okay, no, not really. Okay, let's one less. And then I kind of gauge your level. So it's kind of snappy, quick, and doesn't cause too much upheaval typically. So that's the third one. Then what I also typically offer is a 1-hour written exam, which is also the breadth of things, where I would ask a bit about everything. So kind of similar to the oral exam in that, you know, it's your general understanding of the topics. And then the fifth one, which is maybe even my favorite, is a 24-hour exam. And in the 24-hour exam, it's an open book exam, which means you can use any resource, whatever you find, any books, but it is an advanced topic. So it means that, okay, you think you know the basis of most of the topics, and you're not interested at which level you know it and what do I think about this. You want to go further. That's for the real motivated best students, I would say. And it's like, okay, give me a difficult topic, give me 24 hours, and I'm going to spend probably 10 out of 24 really going deep into this. And one of the reasons why this is my favorite way of doing it is because the exam becomes another learning moment. Rather than being like, okay, now starts the exam, you stop learning. Why? Let's continue learning. That's my idea there. Okay? So those are the options. Again, I'm very open. There is one deadline where I really have to put in the marks. But actually, as we go, we can talk about this, discuss the topics, whatever you think it's interesting. Okay? Any questions about this?
I get everything.
I think that's the kind of the administrative side of things in general. That's what we, are aiming for like that. Okay, so here begins the exam. We begin with the exam in which you learn the most. So let's talk about sound. What is sound?
Hearable.
Sound is something audible. I think that's a good definition. Why is that a good definition? Do you have a definition for sound?
I think sound just some object that they made it like we tap it with
Okay, so that's interesting. So you are involving an object.
yeah.
Does there exist sound without a vibrating object?
No,
Are you sure?
because sound is vibration firstly.
Well, sound is the audible vibration, right? But actually, the sound in itself is vibration of the medium. Okay? And in essence, it is the vibration that your eardrum picks up. Okay? Now, whether there is an objectless sound, is ocean an object? Ocean. Like sea. Is it an object?
Yeah.
Or is it not an object?
It is.
It is.
It is.
How do you define object? Is air an object? Is the atmosphere an object?
Yeah.
Is it?
Yeah.
But there is no solid matter.
Why should it be?
Well, I'm just asking. You see, it's an open question. That's why this is supposed to be an interesting class, because we're gonna tackle these things. Well, ocean is a bit of a medium, really. I mean, I don't know. We could look up the dictionary what they say about an object, but definitely it's not your standard object like cup of tea, right? It's not the kind of object that you can find limits to. I mean, you could say, well, there is the coastlines, but it's kind of huge, and it has sound. Have you heard about cosmical background radiation? So we have radiations in cosmos which are supposedly from the Big Bang, which is again not an object. So I would say that indeed most of the sounds are related to the object, but actually object is also a funny thing if you want to go really philosophical, because it's a process really. I mean, you do say that this cup of tea is an object, but 350 years later, it will not be the same object, but it will be kind of a later stage of the process. 350 years earlier, it was some kind of, what is this, ceramics, some kind of clay, some part of the earth, right? So actually, seeing our environment as objects is a cultural norm more than reality, because you understand that if you take an electronic microscope and you look deep into this teacup, that most of it is empty space. The size of the nucleus of the atom and the electrons are so small in relation to the orbit. It's a bit like planets around the sun, right? So the matter itself is such as well. Okay, we really don't need to go that crazy, but I think it's a good start. So sound synthesis. So typically people say, well, it's creating sound from scratch, which is probably a bad term because you guys know any turntablist? I used to compete in turntablism. It used to be quite popular. Luckily, not anymore. So scratch is a different sound. Scratch is a way of making sound. But indeed, there are multiple physical systems that will produce sound. By the way, I'm really disturbed if you use your mobile phone in the class.
Yeah, I just checked I still have the course in the under 3 p.m. So I just only have 5 minutes. Can I leave just earlier?
Oh, why?
Because we have the course to conflict because I still have another course. But I just didn't.
Which other course?
Music history.
All of you have another course at 3, or
Three,
just you?
Monday. I'm not sure you guys still have. Did you attend music history?
No.
You don't
I
have
mean,
to
I
choose?
received some emails from her, but I'm not sure that we have it today.
Here, this week we have to take it because last week the teachers. have
We
to
know
attend.
exactly when is it,
It's same with the last semester.
but we don't even have it on the timetable.
I don't know. But I received the email.
Where is it located?
Show me, show me.
What's the other?
Just
Just next door?
Yeah, neighbor.
yeah. The classical music building, I think.
Okay, well, I received this as well, but
Yeah.
okay.
Well, it doesn't make sense that I let you go and the other guy stay. So either everyone goes or everyone stays. Because if you are in the same class, so if it's running, it doesn't make sense that you go and they stay, right?
Yeah.
So if you feel emotionally, I'm fine, I can just go for a walk instead. But I don't feel like it makes sense that one guy goes and the others don't. So if you feel emotionally, connected, you can go and check, and then come back.
Yeah, I just worry about because it's the first I received the email and I just worry about that course. Yeah.
Well, you have another course here. You can worry. Maybe you can go there and then worry about this course, and disturb that course by looking in the telephone and being worried about this one. Maybe that's a good option. It's up to you. It's up to you. I just don't want you to go alone and the two guys stay, because if there is a course and it is important, it's important for everyone. If there is a course which is not important, it's not important for everyone. You understand?
I don't think it's
So 2 against 1, you stay?
You claim
it doesn't make
Well,
sense.
she
We
was-
still, it's not even a full group. We have like 2 guys which are absent. Why don't he can just go out for another course if he want, and we can stay.
Well, he can, but I am here only 2 days in the next 2-3 months.
Yeah, I mean, I
And if
appreciate
you-
it, and
huh?
I want to stay for this course.
Uh-huh.
Let him go. Just appreciate your time and.
Yeah, sure. If you want, go. Come on, go.
I just yeah. I'm
Yeah,
sorry
because
about that.
I'm very sensitive because when I teach, I like to have some attention.
Yeah,
And
I-
if
I
you're
know.
distracted already, it's better if you go, obviously.
Yeah, and just I can't manage like the 2 courses at the same time.
No one can. No one can.
Yeah, so
You're not expected to.
thank you for that.
Cool. So, actually, in the physical world, there's multiple ways of producing an audible sound. Okay, so probably the most obvious one is the impact, right? So if you knock against things, things vibrate. What else? What are any other ways of producing sound in the physical environment? Are you guys aware? Well, you can start thinking about physical objects that produce sound. So we have idiophones. right? Those are the instruments that, you know, just have their own sound. What other kind of instruments do we have?
Instrument.
Yeah, because instruments are typically the sound producing
Piano.
tools. Piano, what kind of mechanisms are involved?
Um, the piano wire.
Yeah, there's a string,
Yeah.
but it's also an impact, right? So you have a hammer striking the string,
Exactly.
so it's an impact, but there is a resonator. Okay, so resonators are interesting because they typically make things louder, right? But technically, it is not an accurate way of putting it because, for example, you know, if I have a guitar, there's probably a few damaged guitars around here. So if I have a guitar and there is no body, it will not be as loud. If I put it on the body, the string, it will be louder. So you might say, well, the body amplifies the sound, but that's not necessarily correct because it's a passive system. So how does it work? How can I have a passive system that makes things louder?
You like saxophone?
Well, saxophone as well, you could say, because actually, you know, if I take only the reed and I blow it, well, actually, it could be very piercing, depending on what I do. But indeed, the resonator makes things louder. What happens there? How can a passive system make things louder? So there is two crucial things there. First one is that you have a broadband spectral energy, and you have a system that focuses that energy into specific spectral regions. Because you see, because it's a passive system, there cannot be an increase in energy, right? So technically it doesn't amplify, but perceptually it amplifies it, okay? Now, the other thing is that, so that's one, that's really important, that actually the resonance systems, they don't increase the overall energy, but they focus the energy. So from a noisy signal, you get more pitch-like signal and you get these resonant frequencies, but the energy may not increase. Now that's one thing, but actually if you think about the guitar, the string, as it vibrates, it has kinetic energy, okay? So what we are looking at is this kinetic energy becoming audible, okay? So it means that it has to be transmitted to air or any other medium. And in doing that, if I'm vibrating a string, I will excite the air much less than if I'm vibrating a larger piece of thin wood, because it actually moves more air, okay? So again, the sound that I hear, even though it is louder when there is a body on the guitar, there is not more energy in it than in just the string. It's just that the transmission of this energy is done in a clever way such that more of it ends up being acoustical energy. Okay? So those are the interesting things. I mean, obviously, you know, I'm also trying to lay the foundation for the sound synthesis, as you see, because I think these are crucial, because it's really inspiring as well, right? Because I kind of, you know, I prefer to see you guys becoming inventors, right? More so than, okay, I can just use some synths and I know 10 synths, or I can maybe program some synths. But actually, I think that's the key of deep understanding when you just invent things. You know, and in the context of contemporary musical practice, you know, inventors are typically very welcome as well. And in order to invent something, it's really important to get these basics. Okay, so we have resonance systems, okay, which will transform the energy, make it more audible. We have impact-based sounds. What else? There is one thing. You can think about all the instruments we have, because typically, you know, in the history of music, we have employed all the possible sound excitation systems. Which instrument does not rely on impact, does not rely on resonance.
Okay, so what do you think
Well,
about
this,
flute?
huh?
What do you think about flute?
Flute.
Is it impact?
No, it's not impact. I mean, obviously, if you do contemporary technique, you can do a percussive thing, but it's a wind instrument.
Yeah.
Okay, so it depends on the air stream.
Yeah.
It is a very interesting one because it's not a reed instrument. So with the reed instrument, you have a vibrating reed. So you actually control the excitation mechanism with the air jet. With the flute, what you have is you only have one sharp edge. And that's a really good one to mention because it relies on turbulence. Okay? So turbulence is a physical phenomenon which is the noisy phenomenon. So flute is a very noisy sound. You hear a lot of noise in there.
Yeah.
That's all the air turbulence that's happening in the system. Okay? Anything else? There is one thing which is really interesting and probably one of the most challenging in synthesizing it, because actually all of these things obviously have their corresponding synthesis solutions. We have the slipstick. Okay, so slipstick is a physical principle according to which a creaking door makes a sound and according to which a violin makes a sound. Okay, so that's an interesting one because what happens is as you bow the violin string, what actually happens is that it sticks to the bow and the bow pulls the string along, but when the tension is too high and the grip is lower than that, then it slips. Right? So it sticks and then it slips. It sticks, slips, stick, slip, stick, slip. So that's the stick slip. Okay? So to get a stick slip, actually the chair does that as well, right? If I do this, okay, that's also a slip stick audio or whatever sound producing mechanism. And what it relies on actually is that the energy needed to push the chair from a still stand is higher than the energy needed to keep it going. That's one of the characteristics. And the fact that I can control the intensity of the slip stick by controlling the pressure of the two objects against each other, right? So if I just push this lightly, it didn't creak. I have to push it against and actually find with ratios, with mathematical relationships and such. So yeah, it's continued. Yeah. So you had essentially a situation whereby a composer who was obviously well known or had some impact could have a few technicians who were working for them. So you understand back in the day, so you had oscillators, you had filters, noise generators, basic electronic gear, but actually the recording of it was still tricky, right? So you had the magnetic tape. So typically you had a few technicians, one for the tape, one for arranging the things. And then grand designs were executed, so to speak, in electronic medium. That was the kind of the Stockhausen era and all the rest. And actually, that's where the synthesis of sounds was essentially founded. And it also has to do with, the kind of reductionism, which is a very, solid paradigm still, which means that, if you control all the components, you control everything, right? So that's this reductionist paradigm. If I have information about every cell in your body, then I know everything about your body. Now, this has been, deconstructed. It's been maybe 20, 30 years. Still, it's not very well understood by majority of people. But actually, the science of complex systems has denounced causality in complex systems at a very early stage. In fact, already with the three-body problem in physics, if you understand, if you have gravity attracting three bodies, you already have a chaotic system. You already have the fact that it's only short-term predictable. I can predict it for the next few, days, but mid-term, long-term, it's unpredictable. And we still have the paradigm that if we knew all the details, we would be able to predict, but that's just the remnant of the old way of thinking, and actually scientists are way past that by now. So it's quite interesting to see how actually this whole sound synthesis, comes from this reductionism paradigm, really. Now, one of the things that is similarly of the old age is the conviction, something you might have heard, that you can synthesize every sound from sine waves. Have you heard this before? Kinda. Did you believe it?
Not really.
Not really. Why not?
Well, I mean, we can say that every sound comes from simple sound waves, like a pixels on the screen.
You can or you cannot?
I can imagine, but do you really can produce any sound out of this, just with this information? I don't think so.
Interesting. What's your opinion?
I never heard about that actually.
Ah, yeah, no?
Yeah.
So that's typically your paradigm. It has to do with, again, deconstruction, right? Now, the thing to consider there is that technically, yes. Mathematically, the answer is yes. So actually, we have what we call an orthogonal transform. So we can take a sound. Now, first of all, let me just make a point before I go there, a point about point sources. Okay, so one of the really deeply entrenched paradigms that has its issues is the point source paradigm. And my favorite metaphor to describe the issue is if you imagine an ocean and you're looking at it and it has waves and they're coming and they're changing, the complexity of the surface of the ocean, you observe that visually. Now imagine that I'm going to tell you, I'm going to describe the ocean by taking one point and measuring it going up and down. You see? And you already feel, wait a minute, I cannot describe the ocean by taking one point and looking how it goes up and down. I won't even see the waves. I mean, from our perspective, we probably would agree, well, we can describe the ocean by mapping all the points on the surface over time. Okay, for us, because we don't live inside, it's fair description. But if you're a fish, again, it's not a sufficient description, because how about all the undercurrents and the, whirlpools and whatever is going on underneath? It's not on the surface, right? So actually, the analogy holds. I cannot describe the acoustic environment by taking one point and looking at the variation of pressure. No, it's impossible. It doesn't make sense, right? So the reason why it kind of makes sense is because we seem to have point receivers, right? We have 2 point receivers Obviously, it's a small membrane, it's not the point, but I'm not fussy about that bit. But what I'm fussy about, the reason why I'm fussy about this, is that the psychoacoustical processes are so complex that I can actually tell a point source from a real sound source. If I blind you and I take one of the snare drums, I put it here, record it with the microphone accurately, whatever. I play it through the speaker and then I play it on the drum. You will be able to say that came from a speaker, that came from an actual physical object. So regardless the fact that we have point receivers, our adaptation, our brains have developed such that we can tell very well something about the naturalness and the character of the source. Now, from the physics perspective, the point is that a snare drum or any other instrument will emit different spectral characteristics in different directions. Right? This instrument is essentially made to have some accuracy on axis, right? What happens on the side is typically what engineers don't care about. And actually, that's probably why we can so easily recognize it, because actually the side of it emits a really dull, boxy sound, right? So if I was to cover the front and you would hear only the sides, you would definitely hear, well, that's a really bad speaker, right? We actually recognize the sound of the box as such as well. Okay, so this kind of point source, just remember, it's always hidden underneath. It's an assumption that very few people consider. And it's an assumption that leads to many false claims. Okay, now back to the sine waves. So the point is that, first of all, if I have an instrument, it will emit different characteristics in all possible directions. So I cannot record an instrument. Technically, if you say I record an instrument, it's false. I record the interaction of the room and the instrument with the point receiver in the room. Because you can actually not record an instrument without its environment. That's also impossible. And you're not recording the instrument, you're recording a point receiver signal, which is not the instrument, right? It's only one of those millions of, countless characteristics that an instrument emits. Okay? Now, in terms of sine waves, if you have an audio signal, which means that it's not an actual instrument, it is already a vibration over time, an audio signal, any audio signal can be deconstructed into sine waves and reconstructed without anything missing. Okay, so that is a fact. And that's a mathematical fact because it's a mathematical function. As soon as it's a mathematical function, we trust them to tell us what's up with that. And they know and they tell us. By the way, you can also deconstruct it into square waves. In the same fashion, it's called the Welch transform. So Fourier transform, probably heard that term, is deconstruction into sine waves. And actually you can deconstruct it into any signal and back again. And that's maths. But the issue that we have with this claim that you can synthesize any sound or reproduce any sound or express it as a sum of sine waves is not that whether you can do it or not do it, it's whether it makes sense to do it. Okay? Because there is two classes of sound for which it does not make sense. It really makes sense to do this with a singing voice, with a pitched instrument. But for example, the knock on the table. If I want to synthesize an impact type sound with sine waves, I need an infinite amount of sine waves. Which is just stupid because I can just model the impact in a much simpler fashion. So it can be done, but it doesn't make sense. Okay? And the other class of sounds, maybe you guys can guess, which is really hostile for sine waves. You see, a sine wave deconstruction is something that you're constantly listening to. Anything that your phone plays back, except if it's a WAV file, but it's typically some kind of compressed file, is a bunch of sine waves. So you know, everything you hear, 90% of what you hear is a reconstructed sound out of sine waves. And by the way, there is a lot of removal based on psychoacoustic facts. So it's not even all the analyzed sine waves, but all the analyzed sine waves which should be audible. So actually in the MP3 compression and everything since, which is kind of audio compression, first you go to sine waves, then you remove the sine waves that you wouldn't hear, then you have a lesser data structure, and then you synthesize those sine waves, and then it's your favorite Skrillex, or I don't know what you guys are into. You know, but actually when you listen to something on your phone, on YouTube, everything you hear on Spotify, all of these, everything that is not an actual WAV file or a FLAC is already gone through sine waves. And you are listening to sine waves. You know, so that's obviously why people do go for and say, well, obviously you can resynthesize everything with sine waves because you can compress MP3 from any sound. But if you think about a bad MP3, what do you hear? If I do a 64 kilobyte MP3, like a really bad low quality compression, what do you hear? Can you describe this to me? How is it bad?
It squeezes.
Squeezes what?
Electric sound.
Not a good term. You cannot squeeze an electric sound. You can talk about the dynamics. Were you thinking to say something about the dynamic range? Typically when people say the word squeeze, they mean that the dynamic range is squeezed, which means that it's not too loud and it's not too soft. It's compressed. So that's one way that you can. But what do you hear if you have a bad MP3? What's the audible anomaly that you hear?
I don't know if I ever heard really bad MP3.
No? Well, actually, YouTube sounds like that as well. If you listen to YouTube on these speakers, if you have a good reproduction or decent headphones, you can probably hear. So what happens is that the noise becomes like, you don't get this deep, rich noise, but you actually get a lot of sine waves going up and down. You know, so on a noisy sound, you can discover it. On the transients, you can discover it. Bass is typically lacking definition because psychoacoustics tells us that we don't hear it that well. Spatial detail might be lost. There might be many things that are happening. But the reason why I was asking is because the noise is the second type of, second family of sounds that is just useless when you resynthesize with sine waves. Because again, there is a very simple physical mechanism, turbulence, right? So actually a small resistor in an electric circuit already creates some turbulence in terms of the current flow. It creates audible noise, right? If I do, then I've created some turbulence with the way I've shaped my mouth and the pressure and the air escaping. You know what is turbulence, right? Like in the airplane, you have turbulence as well. So when the flow, so if I have, let's say, if you imagine a river flowing, and you can imagine me putting a stone in the river, and it kind of flows around it. That's not yet turbulence. But if you imagine me putting a stone, and then under the stone, you get these little whirlpools, you get a bit of foam, you get something chaotic going on, that's turbulence. Okay? So in certain situations, you can produce turbulence and it will make a sound, right? Because it is noisy, chaotic motion of particles. Okay? Cool. So back to the sine wave. So that's where it starts from, because the sine, how would you define a sine wave? What is a sine wave? Why is it special?
Basic, ideal vibration. Perfect.
Yes, ideal, perfect. Yeah, why? What makes it perfect? I mean, I like dancing more. It's more perfect to me, or ice skating. Why is sine wave more perfect than an ice skating motion?
Mathematically perfect.
What makes it mathematically perfect? The simplicity.
Maybe.
So what is simple about a sine wave? Because it just goes ups and down with a certain curvature. What are the simple facts about the sine wave? What are the
Looping.
fixed? Yes, it's a wrong word, but you're thinking the right thing. We say it has a strict periodic character, right? So there is a period that repeats. Okay? And typically the period duration determines what? The duration of the period determines the frequency.
Oh yeah.
Okay? So if I have a larger period, what happens to the frequency?
Higher.
No,
No.
lower.
Oh.
Okay? So now the interesting thing is that there is I have to remember again, when I was studying electroacoustics, it was actually at the conservatoire, and the teacher, credit to him, he was having to use the language that everyone would understand. And he was like, look, this is a sine wave. You know, he draws a sine wave and he says, you might think it sounds like wee wee wee, but no, it sounds like wee. And I was like, oh my God. You know, by that time I already knew a few more details about the sine. I was like, but then he repeated it in the next class. Wee 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 wee. So, but the interesting thing there is that there is a sine wave has a fixed constant pitch. Okay? But the waveform is wiggly. So what's constant about this waveform? I mean, the period is constant, okay, but it's still wiggly. So how is that constant? Why does a wiggle give me a constant? The thing that is constant is angular frequency, angular speed. So actually the thing that helps you potentially remember this is if you think about a bicycle and someone pedaling on the bicycle, and if you look at it from the front, you're actually seeing a sinusoidal motion up and down like that. If you look from the side, you see a circular motion. So actually, sine wave does describe a circular motion, but from a single point of view. In fact, if you guys dig into signal processing, probably not, at one point enter the quadratic signals, and actually a sine and a cosine are the two components of the same complex signal. So actually plotting circular motion in a specific way gives you a sine wave. You can probably remember it like that. Or just remember the bicycle, someone pedaling. If you look at it from the front, you actually see the sine wave. Okay? Now, actually, the interesting thing to know is that in analog circuitry, it is impossible so far to produce a decent sine wave. Because any little change about the curvature will introduce harmonics. Okay? So the good thing to say, if someone asks you again about the sine wave, probably a good definition would be that it is a fixed pitch, periodic signal that has no harmonics. Okay? You guys are happy with the term harmonics? What it means? So harmonics are essentially integer multiples of the fundamental frequency. Okay? So if I have a fundamental frequency at 200 hertz, then the second harmonic is 400 hertz, third harmonic 600 hertz, fourth harmonic 800 hertz. Okay? So the interesting thing to understand there is that every circular motion, unless it's exact and perfect, will have harmonics. Okay? So one of the physical systems, actually there is two, that give us sine wave-like motion is a mass spring system. So if you have a mass attached to a spring, what you essentially have is that if you pull the mass, if you stretch the string, you can say that the force is acting, let's say, in the positive direction. Let's say that pulling is positive. The external force acts in the positive direction, and the spring acts in the opposite direction. It pulls it back. If you compress the spring, again, it will be the opposite, what the spring does in relation to the external force. Right? So this actually gives you a system that whereby if you swing it out of the equilibrium, you pull the spring, right? You release it, you release the mass travels back to the equilibrium. When it's at the equilibrium point, it has momentum that carries it beyond, further. Then as soon as it's beyond the equilibrium, the spring starts to act in the other direction, right? So by the time it goes up, it's slowly slowing down, and there is enough force to push it back. And again, by the time it's at the equilibrium, it has momentum to go beyond. Okay? So actually, if you have a mass on an ideal spring without friction, right, without the air, without whatever other loss of energy in the system, you would get a sine wave. Okay, mass on a spring gives you a sine wave. And also pendulum. So like the clock. Pendulum, same thing. If it's an ideal system, physically no friction, it will give you a sine wave. But because things always have some friction, and the same holds in the electronic circuits, in analog circuitry, you do not make a good sine wave. There will always be some harmonics. Okay? So actually, and obviously, this hype these days with the analog gear and all the rest. I mean, I'm a huge analog connoisseur. My analog synth is large. But, typically, it's the kind of modern world. Oh, it's better, then it's better for everything. No, it's not. If you want a clean sine wave, you have to synthesize it digitally. Okay, so the sine wave is quite fascinating like that. Because actually, mathematically, the only sine wave is the infinite sine wave. Okay, so it has a single spectral peak, right? So in the spectrum, by the way, if I say something which is tricky, ask me to repeat or ask a question, yeah? Because this is for you guys, right? So it has a single spectral peak, but if it's not an infinite sine wave, if it lasts for 1 minute only instead of infinite time, it will have a skirt, which means that the spectral peak will start broadening slowly at the bottom. It starts doing this. And you might have seen some spectral analyzers and put some sine waves in, and you might have asked, well, why is it this? Why is it not this? Well, it's because it's not a perfect sine wave like that. In fact, from the perspective of the analyzer, it might be, but actually the analysis is not perfect. And analysis will also give you skirts and ripples and other things, which you probably won't go into. And it's not very interesting for us to, I mean, it's kind of interesting. You can, make a joke about it in the pub. We are big on DSP jokes. If you have a signal processing joke, you're in, you're part of the team. About what's the difference between a sine wave that lasts for a minute and 10 minutes, whatever. That's a bad joke. But unless you have a good punchline for that. But the thing where it gets interesting, that if it's 1 second, okay, we can still hear the pitch. If it's 1/10 of the second, the duration of the sine wave, we are already start to lose the pitch sensation. So a single period of a sine wave, just going up and down, if you listen to this, it's not a sine wave. It's a click. It's an impulse. Okay? So you need multiple cycles of a sine wave to come close to hearing a pitch. And it also has to do with the scale of time. Right? So if I have a 100 hertz sine wave, what is the period duration? You guys know this one. How long does it take for a 100 hertz sine wave to complete one cycle up and down? What's the duration of time?
1 second.
No, 1 second is 1 hertz. Okay, if you have a 1 hertz signal, it means you have 1 period per second. Okay, so hertz equals 1 per second, and second equals 1 per hertz. So that's your reciprocal relationship. Okay? But from there we can get to the answer if you know a bit of math, right? So if 1 hertz is 1 cycle per second, then 100 hertz is
1 minute 40 seconds. 1 minute 40 seconds.
no.
No.
No. So it's 1 hertz. Hertz is amount of cycles per second.
Mm-hmm.
So 100 hertz is 100 cycles per second. So the time duration of a single period is 1/100th of a second. Because you have 100 periods in 1 second,
Mm-hmm.
it means that one period is 1/100th of a second, which is 10 milliseconds. Okay? 1 millisecond is 1,000th of a second. Milli is divide by 1,000. Okay? We don't have centiseconds, but you know, like centimeter, millimeter. Milli is 1,000, 1 over 1,000. Centi is 1 over 100.
Mm-hmm.
And then deci for deciliter would be 1/10. But for some reason, for seconds, we don't have a centisecond. But maybe it's a good term to introduce. We typically talk seconds and milliseconds. So the period duration of a sine wave at 100 hertz is 10 milliseconds. 10 milliseconds. And that in that duration, we cannot establish a sensation of pitch. It's just a click. That's it. You don't hear the sine wave, you don't hear the pitch, right? I mean, I don't know the exact number, and it might differ per listener as well, but I would say at least, well, maybe not at least, but 1/10 of a second is kind of probably the borderline, right? If any sound is cut to be shorter than 1/10 of a second, you're progressively losing the pitch or the character of the sound, and it becomes a click. And obviously, if you shorten it to 1/100th of a second, then it's definitely a click. There is no more character of the sound, no matter the fact that it was the same sound. Okay? So what actually happens is as you are shortening the sine wave, the duration of it, right, it is increasingly a click and less so a sine type sound. And what happens to the spectrum is that it becomes a skirt, it becomes a band, and it becomes flat. So an impulse has a flat spectrum. So, and one way to remember this, kind of, easy way to remember it, if you have an amplifier, a guitar amplifier, and you pull out the cable, click. But if you listen to this, it has bass, it has mids, and it has highs. It actually is a broadband signal. Okay, a click, an impulse, is a broadband. You get this term, broadband? So when we discuss spectrum, right, you understand spectrum,
Mm-hmm.
we discuss spectral bands, which is kind of regions inside the spectrum. So when we say broadband signal, it means that it has a wide spectrum. It is represented across the spectrum. If we have a narrow band signal, it is not represented across the spectrum, but in a small band. Okay? That's why we have band pass filters, right? You pass a certain band. And actually, if you guys want to learn want to use the good language here, you will recognize that, 80% of YouTube synthesis tutorials talk about frequencies when they should be talking about spectral bands. If I say, well, my speaking voice has these frequencies, no, it's not a good term. Because actually the frequency, in its technical meaning, connects to the infinite sine wave. Because as soon as it's not infinite, it's not an actual frequency anymore. And that's the theoretical basis. And obviously, in my lifetime, there's many things that have frequency and I don't live forever. So, there's a discrepancy there. But it's useful to understand the technical underlying principles because that will allow you to understand more deeply facts about sound synthesis. Okay? So impulse is a broadband signal. Do you know of another broadband signal? So sine wave is a narrowband signal, right? What's another really broadband signal? And it's the same answer to the question I've asked before, but it's a different question. Noise, yeah. So fairly straightforward, but I hope that I've kind of dig a bit under the things that you've assumed already, and for a good purpose. Okay, how is your stamina, guys? We're supposed to end at 4, so we do have almost 20 minutes left. So let me just briefly discuss the what I call the geometrical signals. Okay, so we have signals that are derived from maths and geometry, sine wave included, square wave, sawtooth wave, triangle wave. These are your standard things. You probably know this already. Are you aware of how the harmonics of these different waveforms are? There is a difference. You might have heard that some waveforms have only odd harmonics. It's a useful thing to remember. So, and actually the symmetrical waveforms, point symmetrical to be precise, will have only odd harmonics. Square wave and triangle wave. Sawtooth wave is not point symmetrical. It goes up and then drops quickly. And sawtooth wave also has even harmonics. So if you look at the spectrum of things, shall we do a bit of this? A bit of max MSP? No? Let's do a bit of max MSP. I mean, I didn't really plug in the monitor, but you guys are quite close by, so you can see my my screen, because otherwise it's just going to be too much talking. Let me just see, do I have... Okay, display. Why not? Crop, no, show cursor. Well, it's there. Let's just remove it and get a new one. Yes. And...
That's right.
Display. Okay. Okay. So I'll just do this so the video has also insight into what we are doing here. Okay, and then a bit of a talking head in the back as well. Cool. So yes, so I think we will settle with max MSP for these bits. I mean, there are other classes where they're supposed to teach you Super Collider, and if you really fall in love with Super Collider, I will welcome that greatly, and we can transfer as well. Not really. But Max MSP is definitely a more friendly or more accessible, but much more inaccurate, much more inefficient, and all the other crashes and does all the other things as well.
Super Collider is fine, especially for me, as I know the basics of coding, but for others, I don't think it's really interesting.
It could be an issue, yeah.
And
I mean,
it's hard to memorize all the syntaxes when you don't really use it, because I don't use Super Collider.
Yeah, of course, yeah, it's tricky like that. Cool. So sine wave is cycle in Max MSP. And in Max MSP, I think you will have more classes with Max MSP, so I don't really have to take you through everything. But what we can do at this stage is look at the spectroscope and look at the sine wave, and we can give it a frequency 700. And I need to switch